Start.
So in the last experiment, we have given a real-time demo for FIR filter, and we have discussed about all the files that are being added to this particular real-time program. I will once again tell you the list, show the list of files that are added here. So we have done this project, new real-time FIR filter dash project. Open that. So minimize that. These are the files that we have added. This is the source file, source code FIR.c. Already explained you about the logic of this program. So the configuration database file a1.cdb, a1cfg.mcmd, that is linker command file for real-time project, amcsg.h62, a1cfg_c.c. So these are the three header file generated files after adding the CDB file, configuration database file. And I have shown you a path for that's dsk6113bsl.lib also. I have shown this particular path in the last video demonstration. Now once again let us open this program and then once again compile, build and rebuild this program. So compile first, compile is completed, 0 errors are there. So next build the program, then once again rebuild it. Right, now before loading to the program, this is the DSP kit. We have to discuss about the connection, the function, this hardware connections. So compile, building and rebuilding is complete. We have to discuss about the hardware connections now. So you are seeing the DSP kit. I told you that these are the 4 terminals. First one is the MIC in, second one is line in, third one is line out, fourth one is the headphone out. So among these 4 terminals, the second and third are important for us because line in terminal you need to give the function generator input. So you need to connect the function generator input to the line in, and from the line out terminal you need to go to the CRO. So there will be 3.5 mm audio jacks that are there already available in the lab. So these are called as 3.5 mm audio jacks. For this the probe connection is made. So what I am doing now, I am connecting this to the line in terminal of this particular DSP kit. So second one is the line in terminal, give to the function generator. Next, after that one more audio 3.5 mm attached to the probe will be there, that you need to give to the CRO. So third one is a line out. 1 and 4 are not required for us. They are for speech processing applications. I told you already. MIC in and headphone out, they are for speech processing application. So third one you need to give a line out to the CRO. One channel of the CRO you give to the line out, this line out output. So ensure that you are giving the connections firmly. Now give a sinusoidal signal here as input to this particular from the function generator. You need to give to the input to the line in terminal. Give some CRO input as 500 Hz. Approximately you give this as 500 Hz or 450 or 500 Hz you can give it. So peak to peak some amplitude. Amplitude is peak to peak some amplitude you give that. Now next thing is, after giving that, then you go for compile, build and rebuilding. Then you go for loading the program. Inside the kit. So go for file, load program. So whenever you open file, load program, automatically for this one folder name debug will come. Just double click that. So a .out file name having the same name of the project will come. So name of the project is new real-time FIR filter dash project. Here the name of the .out file name is new real-time FIR filter dot project dot out. So just double click that or open that. Click on single click and open. Now the program gets loaded into this one. Without wasting much time, go to the run option. Go to the run option and use the run. Use the run now. Click run. So when you click run, automatically you can observe the CRO output on the CRO here. A sinusoidal signal that is coming on the CRO. So now what you do is in the function generator, this one you vary the signal frequency there. You vary the signal frequency. As you vary the signal frequency, the amplitude goes on. As you increase the signal frequency, the amplitude goes on decreasing like this. You can observe that the amplitude goes on decreasing as you increase the signal frequency. So amplitude goes on decreasing like this. At some point it becomes unstable. After 1200 Hz it becomes unstable, and almost as you increase like that, so on go on increasing like that. Somewhere at after 2 kHz, this completely the waveform will not get the waveform is not visible like this. Okay, so this is actually the function of a low pass filter, which is going to allow only the low frequency component. Only the low frequency component. You can take this one and you can plot the readings also for different things. What are the values of the input amplitude? You fix it. So for different outputs, what will be the output for this? AV is equal to V0 by VI. Actually, how will you plot the frequency response? AV is equal to V0 by VI. VI you have fixed it as some volts or millivolts. Then you vary that frequency from hertz to megahertz. Gradually vary that. As you increase the frequency, the gradually this one goes on decreasing like this. The amplitude goes on decreasing, and somewhere it falls to almost zero after around 1900 Hz or 2000 Hz. So this is so because you have so just come to the program here, because you have designed a low pass filter here with some coefficients, filter coefficients starting from 0.0000, minus 0.001591, etc. These are the symmetric FIR filter coefficients. So they are designed for the symmetric. The FIR filter is symmetric in nature, and it is a low pass filter. It's a low pass filter. And as you decrease the frequency, the waveform gradually raises its amplitude there. You can see the waveform raising in amplitude. Okay. So maybe after 380 or 400 Hz it becomes stabilized. After 300 Hz it becomes stabilized. After 350, 400, 450 Hz it becomes stabilized. You can see that particular waveform on this one. So once again, after varying this particular, after increasing the frequency, this goes on, amplitude goes on decreasing like this. So you can tabulate some readings also on this particular thing. You take an observation and you can tabulate some readings also. So this is a real-time program for designing the FIR filter. So remember that here the source file has to be added. In addition to this, a library file has to be added. The name of the library file is dsk6713 bsl.lib, and already you know the path of this library file also. So CC Studio, C6000, dsk6713, lib. Okay, in this you have to select object and library files. Already explained in the last video demonstration. This is video dsl.lib. You have to add like this. Next, CDB file, you have to go for file new DSP BIOS configuration. Okay, for this you need to go for DSP BIOS configuration. You need to select dsk6713.cdb, then click OK. After that, you need to add that particular CDB file to the project. And whenever you add this particular file, automatically these are the files that are generated. amcfg.cmd, so it's a linker command file that is generated. a1cfg is _c.c. So copy the first line of this header file, it has hash include a1cfg.h into the source file and paste it. And these two header files you need to paste from this one, dsk6713.h and dsk6713_act.h. I showed you already the path for this particular pasting the source file. Okay. So you can go for this particular path, and then C drive, C6 to C, you can go for this particular process C6000, okay, DSK 6713 include, okay, include in this all files there. In this first two files are DSK 6713 underscore .h and DSK 6713 underscore acv.h. You have to copy these two header files and then paste inside the project folder. All these things we have done in the last video demonstration. I am just explaining you as a revision for this particular thing. Okay, so this is the procedure for working out the real-time programs using the FIR filters, the FIR filter program. Okay, thank you.